Alright, so for number 8, it says solve the initial value problem, and it gives us the initial value problem. These are pretty simple, so first what you're going to do is you're going to write the top equation as a characteristic equation. So r squared plus 2r minus 15 equals 0. You're going to find the roots. We can factor this into r plus 5 and r minus 3. And based on that, we can say that r1 equals 3 and r2 equals negative 5. And from here we can build our general solution. So we can say y equals c1 e to the 3x plus c2 e to the negative 5x, and then what we can do is we can take the derivative, and we can say 3c1 e to the 3x minus 5c2 e to the negative 5x. And from there, and the reason we take the derivative is because, where's the laser pointer? The reason we take the derivative is because we're given these two initial conditions, and to apply the second one we need to have the derivative y prime. So from there we can apply our first initial condition to the first equation. So we apply there, and since e to the 0 is is 1, we can get c1 plus c2 equals 3, and now the same way we apply the second one, we get y prime of 0 equals it says negative 7. So now from there we can get again e to the 0 is 1, so we get 3c1 minus 5c2 equals negative 7. And from there, that's just a system of equations. So what we can do is we can, for example, say c1 equals 3 minus c2. Then we plug that into the second one. 3 minus c2 minus 5c2 equals negative 7. We get 9 minus 3c2 minus 5c2 equals negative 7. And we just combine like terms, and we get 8c2 equals 16. c2 equals 2. And then that means c1 equals 1. And so from there, you can use, now we have our constant c1 and c2, and we go back here to our general solution, we just plug it in, and our final solution, or particular solution, what's happening? Our final particular solution will now be e to the 3x plus 2 e to the negative 5x. So number 9 is an exact equation problem. These are pretty cool. So first thing, we're going to define our m and our n. So this is going to be our m, and this is going to be our n. And I know this because our m is always going to be with our dx, and our n will be with our dy. And so first thing we're going to do is we're going to find our partials, so dm dy, and obviously we're going to treat x as a constant, so we're going to get 2x minus 3y squared. We're going to do the same thing, we're going to find dn dx, and same thing, we're going to treat y as our constant, and we're going to get again 2x minus 3y squared. And the thing that makes this, the part that says, explain why the following equation is exact, the way we do that is making sure that these two are equal. So if they're equal, it's exact. Alright, so now we're going to find our fx and our fn. So our fx is basically just going to be m. And our fy is just going to be n. And then our f of xy is going to be the integral of our fx dx. So it's going to be 2xy minus y cubed dx, which is going to give us x squared y minus xy cubed plus, and then we're just going to call it g of y, but this is going to be basically our plus c, because remember, back from Calc 2, this is an indefinite integral, so we're going to always have a constant. And so this gy is kind of key to this whole problem. And so we're going to write down our fy here again. And remember, it's 6y plus x squared minus 3xy squared. And we're going to set it equal to our g of y, or our g prime of y. Or excuse me, let me rephrase that so it makes a little more sense. So we are going to take the derivative of this. We're going to take the derivative of that, and then we're going to set it equal to our fy. So the derivative of that is going to be x squared, and this is with respect to y, by the way, so we're treating x as a constant. So x squared 3xy squared plus, and then it's just going to be g prime of y, right? And we're going to set that equal to, and you can see how this suspiciously looks close to fy or n, right? That's kind of how that's how the pattern will be for all these kinds of problems. And so we're just going to set it equal to fy or n. And so now we can just kind of visually see that our x squared is accounted for, our minus 3x squared is accounted for, which means that our g prime of y is going to be 6y. So based on that, let's just rewrite that here. G prime of y is 6y. Based on that, we can find that g of y, just take the integral of 6y, right? We can find that g of y is going to be 3y squared, which means that our general solution, just go back, where did it go? Up here. It's just going to be x squared y minus xy cubed plus 3y squared, because that's what we found g of y as. And we're going to set it equal to c, some constant. There's going to be, we're basically just combining c's here, so it doesn't really matter, just a constant. And now we can go back all the way up to here, and they've given us an initial condition y of 1 equals 2. And so 1, 2, y of 1 equals 2. And so we can literally just plug both of those numbers in and find c. So we're going to have 1 times 2 minus 1 times 8 plus 3 times 4. And that's going to be, what, 2 minus 8 plus 12. 2 minus 8 plus 12, that's 6. And so now we found C as 6. And so now we can finally get our final answer as this. Yep, that's right. So number 10, it says, find a linear homogeneous constant coefficient differential equation with a general solution, and it gives us a general solution. This one's not too bad if you know what to look for. So first off, what we're going to do is we're going to find our roots. And it's kind of hinted at in the equation itself. So when you see c1 e to the 2x, you kind of know that one of your roots is just going to be 2. So we know that r equals 2. That's one of our roots. And then when you see cosine and sine, you automatically kind of know that it's going to be a complex. It's going to be a complex root. And since our coefficient here is 2, we know that's going to be 2i, plus or minus 2i. And that's it. We don't see any other roots. So those are our 3 roots. And based on that, we can kind of work backwards. So just kind of think about, I hate iOS 26. Just kind of think about what the equation would have to look like, the characteristic equation would have to look like to give you these roots. And obviously for 2 it would be r minus 2 equals 0, and for plus or minus 2i, it's kind of hard to think about at first, but once you realize, you can just kind of do this. So obviously taking a square root of the negative is going to get you I, and since it's 2, it's going to be 4. So if you work backwards, you're just going to get that. So based on that, you can kind of build a characteristic equation. And then from there, you can just FOIL it out. And you get r cubed minus 2r squared plus 4r minus 8. And then that's just their characteristic equation. So you can build a differential equation from there. And you get minus 2 double prime plus 4y prime minus 8y equals 0. And I mean, that's really it. Yeah, this is a linear homogeneous constant coefficient diffie q. That's the right answer.